How about we go ahead and get started? I don't see anybody running down the hall at the moment. So welcome to the camp colloquium for this week. We're very happy to have Sarah Hormozi here today from the Department of Chemical and Biomolecular Engineering. So I want to make sure I get the pairing of words correctly. Sarah's an associate professor in that department who's been here for about a year now. Now I'm bouncing around and does a lot of things in complex fluid dynamics and soft matter physics, and is going to be talking about a number of those things, the fluid mechanics being in the first part there. So bacterial swimming in stress fluids. So Sarah, take it away.
Thank you very much. Good afternoon, everyone, and thank you for attending my talk. Today I'm going to talk about the fluid mechanics of bacterial swimming in gill stress fluids. This is the PhD project of Savarish Narayanan under supervision of Donald Pope and myself. And I would like to acknowledge the financial support of NSF for that. So I'm a new member at Cornell, and I would like to say a couple of words about myself and my research team and what we're doing. So we study a series of complex fluids, and by that I mean inclusions in complex fluids. And the examples are vast. If you think about mud is a paste which is composed of particles. So to understand the impact of natural disaster, we need to understand the initiation of mudslide, landslide, submarine avalanches, the runout and flow dynamics. So we need to understand the rheology of these materials, namely how these materials respond when we apply shear and normal stresses on them, how do they deform. Another example is concrete. In concrete industry, again, concrete is a paste that shear thickens like oobleck. With particles, and concrete is the second most consumed material on Earth after water. And understanding this problem is a huge challenge. Geothermal sciences is another example, and also soft matter is often used in soft robotics in designing tissues or hydrogel for injection. And also we can think of inclusions such as viruses and bacteria in mucosal environment. Mucus is a complex fluid. So the examples are fast. So what we do in our lab, we do experiment theory and computation. And by theory, I mean we make use of applied mathematics method, homogenization, matched asymptotic method, and stability analysis. And why we want to do that? Because the experiments that we do are really advanced and expensive. We don't want to do any experiment without knowing the answer. So, also we have to set up artificial computations because it's really difficult when we do experiment in real world problem. There are nonlinear coupling of many things, and it's often very difficult to understand what's happening in the experimental world. So we have to set up well-resolved computational basically platform that we would be able to artificially switch off and switch on effects to understand what's happening in our system. To give you a couple of examples, so the current research projects that I have can be divided in three categories. So the soft matter design and rheology that touches on the open questions in physics of condensed matter physics. Clean energy and mainly geothermal sciences. As we know, we want to go green on campus Cornell. We want to extract heat from the ground and heat the campus during the winter season. So this is a project which scientists all over from chemistry, engineering, and earth, ocean, and sciences involved. And this is basically a project that I've recently started, and I was motivated by the pandemic, and I wanted to understand the fluid mechanics of viral and bacterial diseases, and that's what I'm going to talk about today. And it's about the motility of bacteria in complex fluids. So before proceeding with my presentation, I would like to introduce this community, the Cornell Soft Matter Hub. So it's we established a group, a very large group from Cornell campus, all over departments, chemistry, physics, engineering, biology, that we talk about the problems in soft matter. And it's for this semester, every Tuesday, 1 to 2 p.m., we have soft matter discussion. Please check out the website, and would love to have applied mathematicians in that community. If you're PhD students looking to be a professor in years to come, you would get lots of neat projects to think about and apply your mathematical techniques to. So, so this is the outline of my talk. It comes into 3 parts. In the first part, I would like to give an introduction about bacterial locomotion in biological fluids. In the second part, I'm going to talk about non-continuum biological fluids and the effect on bacterial motility. And the first part, I'm going to talk about non-Newtonian behaviors of the biological fluids and how those affect the bacterial motility. So this is the first part of the talk. So to give you an introduction about the topic, so let's start with the governing equation of motion for fluid flow. So if the flow is incompressible, if the density is constant, this equation tells you the mass is conserved, the divergence of velocity field is 0, and this equation is the second law of Newton for the motion of fluid, and that tells you sigma F is equal to ma. So the left-hand side is mass times inertia, and the right-hand side is the summation of forces, and that could be pressure, viscous, gravity, whatever you have, so on and so forth. But there is an important dimensionless number here that is called Reynolds number, and that is the ratio of the inertial stresses to viscous stresses. At the scale of bacteria, Reynolds number is very small. It's vanishing. Therefore, we can drop the left-hand side, and the left-hand side in a Newtonian fluid is the source of nonlinearity in the problem. So we're going to drop this, and the resulting equation is called the Stokes equation, and that is basically sigma F equal to 0 because we drop the inertia. And so in that case, you can see the equation is linear, and there is no time dependency. As a result, it's reversible, meaning that any style of motion like a scalar is not going to work in the low Reynolds number flow, because as you reverse the boundary forcing, you reverse the motion, the velocity, and as a result, the net displacement would be 0. So for a microorganism to be able to swim in a low Reynolds number flow, it should overcome the reversibility issue. And here in this movie and picture, you can see a bacterium, E. coli. They have a head and they have a tail, and the tail is like a handed screw, and they turn it in one direction without reversing the motion, and as a result, they produce they overcome the reversibility issue. And also, there is another important thing here, is that if I have a filament, and if I move this filament in an axial direction in a linear fluid, in a Newtonian fluid, it experiences half of the drag or resistance compared to the fact that if I move it in a transverse direction, okay? So that anisotropy in drag helps the bacterium, the flagellum, the helix, as it rotates to produce a propulsion force. And of course, everything is force-free in low Reynolds number flow, so this force should balance by the drag force on the head, okay? And that's how they swim. So, however, microorganisms, there is no however here, so microorganisms have evolved to be able to swim in biological fluids. And biological fluids are complex fluids. I'm going to talk about them in a moment. So these are the examples of sperm cells in cervical mucus. It's actually from Cornell. Sperm moving in a Newtonian fluid. You can see that the behavior, I mean, the shape is completely different than if you put it in a viscoelastic medium or a mucosal environment. Or in lungs, cilia interact with the mucus and those filaments kind of produce propulsion force. And this is another example of the H. pylori bacteria that they move into the mucus of gut, and they cause stomach ulcers. So because of all of these examples, people in the community, scientists in the community, are really interested in studying the motion of these species in complex fluids such as viscoelastic fluids, and they want to look at it from a continuum point of view. They want to look at the whole biological fluid as continuum. And the simplest way that I can explain what viscoelastic fluid means is that consider this dashpot and a spring. As you stress it, you store some energy in the spring, but you dissipate some energy into the dashpot. And viscoelastic fluids, such as mucus, they have that property. But as a result of this elastic behavior, the relationship between stress and the velocity gradient, or shear rate, is not linear anymore. So even Stokes' equation, which sigma f is equal to 0, you put this nonlinearity into here, the equation is no longer reversible, and it is no longer linear. Okay? So a scalar can swim in this environment. And so because of that, the main questions that are raised by the community were, does viscoelasticity enhance or reduce the swimming speed? What is the nonlinear coupling between the kinematics of the gate and the rheological behavior of the fluid, and so on and so forth? Yes?
What exactly is that triangle thing? Is that like the convective?
This is the upper convected Maxwell derivative. It's like that you put your frame of reference on the fluid element and you move with it and rotate with it.
Okay.
Because the formation is very large here. And what I want to do now, I want to step back. And I want to ask the question, what exactly mucus is? And what is the rheology of it? And what kind of microstructure does it have? And are we allowed to consider that as a continuum? So this is the mucus is composed mainly of water, and another element that is mucin fibers. And mucin fibers are these long biopolymers of 3 to 10 nanometer width and 10 micron length. And they kind of interact with each other to make a mesh. And this is the scanning electron microscopy of the mucus. And you can see that in nanometer size, this is the mucus of pores, you have this pore structure. Okay, so even if on the bulk it's a continuum gel and it's self-evident, in nanoscale you have this pore size for horses of order of 500 nanometer, but for humans it's of order of 100 nanometer. So it's not really at this scale continuum. So it's a discrete medium. And also what I want to say is that if I perform some rheology and measure the elastic and viscous properties of the mucus, well, I mean, these are some rheological curves, and I don't want to talk about them. I just want to give you the key message. So we can see that the elastic property of mucus is much more than the viscous property, so it's more solid-like than fluid-like. And also if we impose stress on that, you realize that the behavior is like a shear thinning behavior, meaning that as we shear, the material viscosity drops, but there is a threshold in a stress that we have to overcome to be able to deform it. And again, it's self-evident to everyone in the room. And that threshold is called yield stress, and this is often forgotten by the community. And I tell you why. So the simplest way that I can explain to you what yield stress or an ideal viscoplastic model is as follows. So if you had a Newtonian fluid, a linear fluid, the shear stress and velocity gradient, they have this linear relationship. In a yield stress material, in a very ideal way, you can think of it as there is a stress below which there is no deformation. Shear rate is 0. And above that, the material can behave like this. And so you have to overcome the second invariant of a stress in the field to be able to deform this material. there is so that kind of this is a very ideal mathematical law that has drawn lots of kind of attention by, mathematicians really like it because they can work on the existence and uniqueness of the solution to this problem. And I think this singularity is a very nice mathematical thing, computational and theoretical thing if you want to think about it. I'm going to talk about it a little bit. But there is an important dimensionless number here that is called Bingham number, and that is the ratio of the yield stress to viscous stresses. So when Bingham number goes to 0, you recover linear Newtonian regime, and when it goes to infinite, you basically go to the limit of viscoelastic solid, which I'm going to talk about. So what I want to conclude out of that, first of all, this singularity and the yield stress effect is really important because that shows the onset of motion. If the bacterium wouldn't be able to overcome that stress, there is no motion. So that singularity is really important, and we have to take that into account. Second of all, swimming in continuum viscoelastic medium and forgetting about the microstructure is erroneous, and I tell you why. So let me remind you about the structure that was like a porous structure, and for human it's about 100 nanometer. And if you look at the scale of E. coli, the bacterium, so the head is about 1 to 2 micron size, but the tail is, the diameter of the tail is 10 nanometer. Meaning that the tail really whips in these pores, but the head sees the continuum and sees a sticky gel to move through. And so this is something that when I looked at the literature didn't make sense to me, and I thought this should be this way. And I found this beautiful experiment by Wilson Poon from the University of Edinburgh. They measured the viscosity that the flagellum sees, and they showed that this viscosity basically is the viscosity of solvent, which is water. And this is just the swimming, not in a mucosal environment, swimming in a very dilute polymeric solution. But the hypothesis was that the flagellum carves a channel of water void of polymer, and they kind of whip in the water. So this is what I want to talk about. So this is just very preliminary. We've started this project in a couple of months, so I really don't have that much to talk about. But I want to raise 2 questions and answer that. So the first, the second part of my talk is about the non-continuum effect, the discrete effect that is seen by the flagellum, and the third part is about the effect of yield stress and elasticity. Yes?
So do we assume that this mucus structure is stable, so like you cannot move and the flagellum is not going to move it around? Or like, is it something like a fixed structure is not going to move at all?
We don't know. We don't know because I'm going to talk about how we formulate it mathematically, but we need to have experimental observation. There are different ways. You know, you can. Okay, I'm going to talk about it. If I don't, we can discuss after that. If I don't, if it doesn't come up in the slides, let's discuss about that. But that's excellent question, and that's going to come up. So non-continuum effects. I'm going to raise 2 questions, and I want to see how if we can answer that. The first one is, how does the structure of polymeric fluids interact with the flagellar bundle and the head of the microorganism? And the second question is that how is the motility affected when at the flagellum scale, bacteria don't see a continuum polymer solution? So this is how we're going to think about this problem. Of course, we need experimental validation here. So I'm going to assume that the head is a sphere and the tail is a helix, okay? And we're going to say that we're going to consider the polymer phase, the mucins fiber, and the solvent, the water. They are 2 interacting continua. And we're going to consider each phase as a fluid phase and solve the governing equations of motion for each of them. So we assign velocity field and pressure field to each of them separately. But the way that they interact with each other is via a drag force Okay, so the bacterium, the flagellum, you can think of it as it imposes stress on the solvent, and the solvent interacts with the polymer phase through a drag force and kind of and drag it along. And therefore there is a slip velocity between these two phases, but the slip velocity goes to zero, or the difference between the velocity of two phases goes to zero as this over a length scale that we call it Brinkman screening length scale. And we can write down the second, the conservation of mass for both phases, and the sigma f equal to 0 for each phase, okay? What I want to say is that I'm going to assume everything is linear, because my goal is to just address the non-continuum effect, okay? When we talk about nonlinearity, yield stress, and elasticity later. So we're going to solve those equations, and if everything is linear, we can solve them theoretically. And I want to consider two scenarios. And in one scenario, I would say that the flagellum imposes a stress on the solvent. The tangential stress on the polymer phase is 0. But then the interaction between the polymer phase and solvent phase and the drag would kind of cause the polymer phase to move as well. In the second scenario, I'm going to assume that there is a depletion layer. There is no polymer here. Okay, it's just solvent. And I'm going to just solve the governing equation for the solvent here. Outside the depletion layer, I'm going to solve the equations that I just showed. At the interface here, there is no tangential stress on the polymer, but the polymer, the depletion layer, the bacterium want to keep the polymer away. It's like that you're walking in a pampas field, and you kind of push everything away, and you want to walk. The larger you push, the more difficult your walk would be. You have to spend more energy, okay? So that's this condition that I'm going to formulate and apply. So, and also one more thing, if I understand how a sphere moves in such a non-continuum two-fluid model, and how a cylinder moves in such a continuum, I can glue the pieces together and understand how the whole microorganism can move in such an environment. So this is the result of the sphere moving with no depletion in such a medium. And of course, this is the drag force on the sphere, and the drag is normalized by the drag force of the sphere moving in a pure solvent. And you can see that this is the result as a function of the Brinkman length screening. I'm going to talk about it, I'm going to explain it in a second. But first of all, it's obvious that if I increase the viscosity of polymer, the drag should increase, okay? But if I look at this decreasing trend, at the limit of LB, or the Brinkman screening going to 0, it means that there is no slip velocity. It means that I have a mixture of solvent and polymer. Okay, so we recover the drag on that part. And at the limit of LB going to 0, it means that there is no LB going to infinite. This length scale of the slip velocity going to 0, it means that there is no interaction between these two continua, and basically there is an additive drag of two cases. But because I assume that there is no tangential stresses on the polymer phase, it's like adding a sphere moving in a solvent plus a bubble moving in a polymer. So that's gonna drop. And another case, I mean, the case would be the same, the reasoning would be the same, the trend would be the same if a sphere rotates in such a medium as far as torque is concerned. So the larger this length scale, the smaller the torque. So now consider the case that there is a depletion layer. Okay, as a function of Brinkman length screening, everything's the same as before. But what I want to draw your attention to this time is what happens if you increase the depletion layer. The larger the depletion layer, again the pampas field, the larger the depletion layer, the drag is larger because there is a huge normal force that is developed in the polymer phase to keep the polymer away from the sphere. So the drag, the resistance to normal motion goes up as we increase the depletion layer. However, as we increase the depletion layer and we rotate the sphere, the torque drops. And that's clear because we said that there is no tangential resistance to the polymer motion. So the larger the depletion layer, the sphere doesn't see the polymer at all. So it's like it's rotating in pure solvent. Okay? So what I want to, so now we have these pieces, right? What if I have, and we've done this for the cylinder, and we got the same kind of results, qualitative results. Of course, quantity would be different, but the conclusion is that the resistance in such a medium, the resistance to normal motion is huge, but the resistance to tangential motion is low. And now that we have all of these pieces, we can kind of put everything together and understand how a microorganism swim in such a medium. I don't have an answer for you to tell you if the swimming speed goes down or up. I envision there are possibilities of both scenarios. And there should be, I imagine that there should be some limits that a bacterium can really swim faster because the normal resistance is larger than the tangential resistance. It means that I increase the anisotropy in drag. That's how, and that might be helpful for some regime. So it's still left to be done by Savarish. So that was the first part. The second part. In the yes.
So I'm not sure if I completely understand still. Do your equations predict the existence of depletion layer, or are you just asking?
So no, the reason we have to do it, one part of this project is experimental work, and it is very challenging because the bacterium, the flagella, is of the order of one protein molecule, and resolving that spatially and also temporally, because it whips with it rotates with the frequency of 100 Hertz. It's a very, very difficult experiment to be done, and I don't know. These are my imaginations, our imaginations, I should say. And the reason for these imaginations are because of the experiments that we observed by the physicist Wilson Kuhn. What they've shown is that they measured the viscosities based on some measuring the swimming speed and the rotation of the head of the bacterium. They kind of did the math and figured out what kind of viscosity would give that swimming speed and rotating speed of the head, and that kind of tells that this is like that the flagella whips in water. And again, this is another imagination that if it whips in water, it is possible that it carves a channel of solvent, a void of polymer, and that moves in that channel. So that depletion layer that we are considering here is at the outcome of such imagination, which is actually, there is an evidence experimental measurement that is true. But our plan is to really visualize it.
Do you think there's like an easy quantitative model for describing how a depletion layer would be created? Because like right now you have like conservation laws that say that there's no creation or depletion of these things. So.
Yeah. So I think what we have to do is that so what I'm assuming here is that the concentration of polymer is constant. It's a big assumption, right? That if it whips in water, it might create around it the variation in the concentration of polymer. Okay, that means that I have to take it into account as well. We know how to do it mathematically. We know how to formulate that problem, but we need some experimental observation, and also we know what is the diffusion time scale of these polymers, right? So if you kind of whip in these environments and create a void space for yourself, you need a time scale of diffusion of the polymers for polymers to come back to this space. And if the time scale of motion is kind of much faster than the time scale that these come back, so this scenario is physical. But we can formulate it, but we need some observation.
Okay, thank you.
Yes?
Here, in your equations that you showed, is there already a term for diffusion of polymers?
No, because I consider the concentration of the polymer is constant. If I release that assumption, that would come into play, because then the incompressibility of the velocity field is going to go away, and I have to bring into account a diffusion osmotic pressure, let's say,
In the momentum equation?
in the continuity equation, right? In the conservation of mass, because now that the volume fraction of the polymer is not the same, right? And if you define in a volume average the volume fraction times the velocity will give you the velocity that will come into continuity equations. Okay. So the second part of this, the last part of this talk, I'm going to raise this question: how does the motion start? If you put a bacterium in such an environment, how does the motion start? And then how does the interplay of viscoelasticity and yield stress affect the bacterial motility? So how does the motion start? And I want to bring nonlinear effects into play here. As I mentioned, the mucus has a yield stress. So for the motion to get started, the microorganism should overcome the yield stress. And the way that it works, there is a flagellar motor inside the head of this microorganism that imposes an identical torque, but opposite in direction, to the head and to the flagella. And the question is that if I have such an object, if I impose two identical torques, does the head rotate first or does the tail rotate first? That's the question. That's the onset of motion. And again, you can think of the tail as these cylinders, okay, locally. And I want to understand if I impose a force at an angle to this cylinder, what would be the resulting velocity, and at what angle that velocity would be. So these are the questions. So this is, I'm going to answer the filament. So there's a beautiful work by Neil Ballenforth and Duncan Hewitt in JFM. I'm going to grab a couple of slides from them to explain to you the motion of the cylinder. So suppose that you have this cylinder in a beam complete, in a very ideal viscoelastic fluid, and what you're asking is that if I apply this velocity at an angle, so that the cylinder can move in a transverse and axial direction, what would be the resulting force and at what angle? What I want to tell you is that there are theoretical limits of this problem. In the limit of very large Bingham number, basically the first term drops, there is no deformation in the material, and you approach the plastic theory. And then if you assume that in that limit your stress, the second invariant of your stress is very close to yield stress of the material, you can, the momentum equation with this kind of condition, these are set of hyperbolic equations that we can solve those theoretically with the method of characteristic. Okay, so you have some theoretical handle when Bingham number or yield stress is super large, very large, and then Bingham number goes to 0. You recover the Newtonian limit that you can make use of Mash asymptotic technique to solve this problem theoretically. But in any finite value of Bingham number, there is no theoretical solution, and we have to solve this computationally. And I'm going to show you the solution. So here, from left to right, I'm going to increase Bingham number. You can think of it as I'm going to increase this yield stress. So when yield stress is very small, you can see that you're in Newtonian regime. And I'm going to just solve the problem that this cylinder is moving in a transverse direction. So basically phi is 0. There is no axial motion. So when yield stress is small, you can see that you're looking at the deformation, the shear rate, deformation, the velocity gradient in this color map. And the stresses decay, and at some point far from the flagellum or the filament, they go below the yield stress, and everything plugs up. And as you increase the yield stress, you can see this region is becoming more and more localized, okay? So the stress decays fast and goes below the yield stress in a region that is of the order of the size of this filament. And in addition to that, so here there is no deformation. You have some islands or pockets of plug region that are created around the filament. And you can, basically there are some boundary layers that the deformation is huge, here and here, and we can solve the solution in those boundary layers. There are self-similar solutions, so you have some, again, theoretical handle. But the key message from this is as follows. As you increase the yield stress, the stress becomes localized in the vicinity of the filament, okay? And if you calculate the drag force in the limit of very small Bingham number, you can basically use match asymptotic method, so you can calculate that theoretically. And in the limit of very large Bingham number, you can solve the hyperbolic equation using the method of characteristic, and again figure out what the drag would be. So this is one case, but then so this is the case that I just showed, that the filament is having the transverse motion, and that was the stress field or shear rate around the filament. But there is another basically extreme, that this phi angle is now pi over 2, which means that the filament moves along its axis. And in that regime also we can solve the problem theoretically, and you can see that the solution is really, really different. I mean, it's like that there is a sheet of yielded material around this rod. It's like some kind of shear layer, and the rod is moving through that, and the rest is just, it's plugged up. There is no deformation. And now, if you know these two limits, you have to ask this question: what would happen at different angles? At different angles of the velocity, what would happen? So you know what happens to this motion, you know what happens to this motion, so now what happens if you tilt this rod and move it in this medium? And you can see that as I tilt this rod, the form of the solution really doesn't change that much until I really get close to this pi over 2. So if I plot what would be the resulting angle of force as a function of the angle of the velocity. So in the limit that it's transverse, so the angle is 0 for the velocity, and it should be 0 for the force. When it's perpendicular, that should be the same for both. But as Bingham number goes to infinite, or it becomes very large, you can see there is a boundary layer here. What does that mean? It means that you're moving along the axis. You tilt this a little bit, and as you tilt it a little bit and you want to move it, so you move it along the axis, you tilt it a little bit, what happens, the angle of force kind of spins away a huge amount around this. So that's like a boundary layer. So if you want to understand what's happening, there is a huge drag anisotropy. The drag, the resistance to the transverse motion for such materials is by far larger than the axial motion. This is much more than what we have in Newtonian. And you can play with that, and I'm not going to go into detail of this figure anymore, but you can do the math when you drop the rod like this, or when you drop it along its axis, and you ask this question, what would be the force that you would overcome the yield stress and initiate the motion, and that's called Oldroyd number, and what is the critical Oldroyd number, and if you do the math, you would see that the critical force that you need to overcome a yield stress to make a transverse motion is 4 times larger than to create an axial motion. And for a case of Newtonian fluid, it's twice, as I said at the beginning of my talk. So the huge drag anisotropy. So you can try it and kind of drop your a rod in your favorite viscoelastic fluid, yogurt or chocolate, something transparent to see what would be that. So that we know. Again, now I'm going to talk about the head problem. The head is a sphere, and the question is that if I apply a torque on this sphere and rotate it, what would be the critical torque that I have to apply to overcome the yield stress? And again, we can solve this problem theoretically and come up with a critical Oldroyd number. It's a nice boundary layer problem, and we can do it with the regular perturbation method. Again, we conclude that the critical torque for rotating a sphere is 4 times smaller than making a transverse motion to a filament. So now we have all of these. We know how much force we have to apply to overcome the yield stress for both the head and the tail. So what we're going to do, these are some data from the experimental measurements. So we know what is the radius of the head. We know what is the torque that the motor, the flagellar motor, can apply on the head and on the tail. We know what is the diameter or the radius of the tail, and we know what is the size of this helix. So we have everything, and so we can say that if the motor kind of applies this torque on the head and the helix, which one would rotate first? So we can, if I have the torque, I can divide this torque by the area and the R, the lever R, and I can get the stress, the characteristic stress on the head. And for the flagella, we can divide this torque by the lever R, which is the radius of the helix, and the area of the tail, which is just the area of the long, circumference area of the long cylinder. And if we do that for a mucus with 0.1 Pascal, this the Oldroyd number for the cell is less than the critical Oldroyd number that we calculated. So everything's fine. The head can rotate, and the bacterium also can rotate. And actually the characteristic stress on the tail is much larger than the head, and the motion of the helix is easier, even though the critical Oldroyd number is larger. But if you increase the yield stress, again, 1 Pascal can be the yield stress of a healthy mucus. And you can see that this time, because the head is large, the characteristic stress on that is small, and it goes below the yield, the threshold that you need to overcome the yield stress, and the head gets stuck, but the tail moves. So there is a scenario that this scenario is possible that the motor applies torque, but because the head doesn't have enough stress, it would get stuck, and the tail rotates fast. It's like pulling your car out of the driveway in a snowy day in Ithaca. So the tires rotate fast, but the car doesn't move because the car cannot overcome friction. So that's how it works. So now, any question? the second question that I want to answer is that, well, okay, does this thing move at all? Even if it overcomes the yield stress by the rotation, can it overcome the yield stress during the transverse motion and it moves? So what I want to show this was a totally separate problem that I solved for a totally different reason, but I want to make use of the result of this paper and just provide some data or what I think. So there's a problem that we solve. I'm very interested in understanding what is the shear-induced sedimentation of a particle in a gel. Okay, so we wanted to know if I put a sphere in a gel and the gel has elastic and plastic properties, as I shear that, what would be the sedimentation of that sphere? So we solve this problem for an elastoviscoplastic fluid. So these are the governing equations. So the simplest way that I can explain these governing equations is as follows. So I have a medium that if I overcome a yield stress, the medium behaves like a viscoelastic fluid. But if I don't overcome this friction or yield stress, the medium behaves as a viscoelastic solid. Okay, and we solve this problem of the sedimentation, and we realize that so these are the stress on the sphere, the pressure and the different components of the shear stress on the sphere. We realize that as we increase the elasticity of the medium, there is a huge anisotropy in the pressure field, and that would reduce the viscous stresses, and eventually it reduces the drag. So, so elasticity favors motility, and then I was talking to Susan Suarez in biology department. She's retired now. She said that if I want to summarize my whole contribution to the field, I would say elasticity favors the motility, and the computation results show the same thing. So we went ahead and we calculated this problem. We said that, okay, so assume that I know what is the drag on this head of the microorganism swimming in an elastoviscoplastic gel. I'm going to assume that the tail whips in water, so the tail can kind of have a range of propulsion force. And the question is that as I increase the elasticity, what would be the yield stress above which there is no motion? And we realize that as we increase the elasticity, the threshold in yield stress increases, meaning that the more elastic the material, the larger amount of yield stress it can stand and it can overcome. And again, when the motility, I mean, after yielding criterion, after the motion gets started, the motility, the drag actually decreases as a function of the elasticity. So if you increase plasticity or yield stress, drag coefficient goes up. But if you increase the elasticity, drag coefficient goes down, and that would enhance the motility. So we have all of these numbers, and we said that, okay, so for bacterium, we measured experimentally that the tail produces 1 piconewton of the thrust, and we kind of extracted all of these data from healthy mucus, and we said that, so based on this result, what would be the swimming speed? And the swimming speed is 0.05 micron per second, which is 100 times smaller than swimming in a Newtonian fluid. And however, this is actually this is good enough for the bacterium to swim a 10 micron layer of mucus in 200 seconds, which is smaller than the clearance time scale of the mucus in airways. So they can really be an element to infect the epithelial cell. They can really reach into the time scale. But the problem that I just showed you is very is simplistic in a way that I assume that I know that the force and what would be the swimming speed. That's the problem. The real problem is like a force dipole. because the center of the action of the drag on the head and the propulsion on the tail, they are not at the same point. So a forced dipole in a flow field has a totally different stress distribution than a single force. And that the question is that what is the interaction between the head and the tail, and how this interaction enhance or reduce the yielding. And you have to really include that into effect, because we're talking about a singular material, and if we don't include all of these interactions, we won't be able to capture the onset of the motion, because it's a singular thing, right? So what we want to do, the next step, is to just solve the real problem, and the real problem is as follows. So the head is not spherical, it's really ellipsoidal. So what we want to do, we want to combine the computation and the localized perturbation method, or the MASH asymptotic method. So in mathematics, localized perturbation method, you have a strong perturbation in a very, very tiny area. You can do singular perturbation to match the solution. So what we want to do, we want to assume that the tail is like an infinite cylinder. We can solve the governing equations, Stokes equations around the tail, and of course considering the non-continuum effect. And then in the outer region, we're going to solve the solution for an elastoviscoelastic gel computationally, and kind of match these two solutions together. And also we need experimental data, we need experimental validation. So what interesting part of this project is that for experimental data, we cannot really use the mucus of human, because from one person to another person, mucus property will change. So we are collaborating with the group of Dean Archer. Liska is the PhD student who is helping us, and my fantastic undergraduate student, Katie, and they're working to come to design an artificial mucus, and we want to do that with again, that's going to be soft matter design of nanoparticles plus polymers hairs on the surface of them to come up with a mucus that will have the same pore structure and the same rheology, and also we want to have a handle on the properties to make these things really move. We want them to. But to summarize, in the first part of the talk, I hope that I could convince you this problem is a non-continuum problem, and the medium that is seen by the head is really different by the one that is seen by the tail. And the second part of the talk, we came up with some mathematical formulation based on two fluid medium to understand what would be the role of non-continuum effect. Of course, we have to kind of glue all of those results to understand what how a microorganism does in such a medium. And in the third part of the talk, I showed you that elasticity favors the motility, and we hope that to solve the real problem, which kind of include all of the interaction. So thank you for having me here, for listening to me, and these are the references for the talk.
So we do have a few minutes if anyone has additional questions after the talk. Get started with one from sort of the last part. We mentioned building synthetic, because you're having, I guess, a more controlled environment. But I'm just curious, I guess, for how hard is the imaging problem, or the actual, getting sort of measurements you then trust to match to the sort of hypotheses in that setting? Is that sort of, I guess, are there any challenges there as well?
So this movie, the first movie that I showed, that is from Howard Berry from Harvard. I don't know how many people appreciate this movie, but it's not old. We're talking about 10 years or maybe 20 years. but it's just recent. But for years, we knew that these organisms move, but we couldn't see their tail really. So it's a very, very difficult kind of visualization, because the way that we are looking at it in this picture, for example, you would think that the tail is much thicker than what I say, because this is 100 times smaller than this. But the reason is that they have added so much fluorescent dye to the tail that you would be able to see it, and the head really doesn't have that much. So it's a very difficult problem, and we are collaborating with Wilson Hood at the University of Edinburgh, because after Howard Berg at Harvard, he knows how to do the advanced microscopy on these things. Because we're talking about watching the tail is basically a protein, molecule of protein, which moves in 100 hertz. So if you really want to go down and resolve a scale of 1 nanometer or even less, that's a very small scale, but then the dynamic is also fast, which is very, very challenging to do microscopy of these things. But they got it. They know how to do it, and we want to do that. The idea is to also fluorescent dye some of the mucin polymers and see if we would get lucky that it would come to our experimental window to observe that interaction. But if that we know how to formulate mathematically, but the more, but the models could be very sophisticated, and we don't want to do those sophisticated models unless we have to. So we have to do experiment, and that's the part of this project. So, half of this project is experiment.
So the picture that you showed wasn't so big a section of the mucin network, so it wasn't so easy to tell. But is the mucin network something that you realistically think of as being effectively, isotropic in a homogenized way, or is there enough shear flow types of effects that you might have anisotropy because of directionality in the mucin network in actual biological fluids?
Yeah, that's a great question. I don't think it's an isotropic medium, and I don't think, and also one thing that I removed in all of this problem is just I removed the background shear flow. I mean, if you think about the flow in airways or the flow in intestinal area, there's always movement, right? And that movement actually is in favor of the motility, because that movement and that anisotropy makes this material to yield, and if it yields, the bacteria can move. But this is very interesting that there is a dearth of data when it comes to mucus, and it's because sampling is very difficult, and most of the, when I was looking into the literature, most of the data that we have about the property, even the anisotropy that we're talking about, they correspond to the people with cystic fibrosis disease, which the mucus for them is very, very different. It's super thick. The yellow stress is like 100 to 1,000 times larger than a healthy human. And it was surprising to me that it's just, we don't have that much data. And the data goes back to 30 years ago, where the instruments were not that advanced to measure all of these things in a systematic and proper way. I mean, as far as signal of the instrument is concerned. And I think this is just something that is good to look at. And I think that's another reason that we wanted to design our own artificial mucus, because we wanted to have a control on that. And from one person to another, I mean, things change. So it's, even if you report it, the results might not be reproducible.
Is there enough understanding of the properties of the mucin polymer that one could do a molecular dynamic style simulation to try to get at any of these questions, or is that just
No,
we don't
that's
have
a
enough
That's a great question. One of my colleagues, Matt Peshek in our department, he's expert in mucin. One thing I think what difficulty in simulating, in applying molecular dynamic simulations to such system is that the diffusion time scale is so small that causes problems. So you have to integrate across a very long time scale, and I think that's a very stiff problem to solve, a real problem with molecular dynamic simulation. So for the artificial mucus that we have in mind, so we're thinking about it with Professor Hope that if we can do the molecular dynamic simulation, but it should be a very stiff problem. We have to come up with ways. So we have to make that's just challenging.